We're back. And this was the last slide that we talked about in the last lecture video. And it was this whole concept that we had to make the organometallic in order to use the organometallic. And we went through two organometallic compounds at the same time because they're very similar. And that was this whole Grignard, which was a magnesium based organometallic, and the lithium based organometallic. The difference, the lithium, we needed double the amount because one of the lithiums had to go onto the organic while the other kind of sidetracked bromine off in the distance. And the magnesium just didn't care. The magnesium just grabbed a hold of the organic and grabbed a hold of the bromine and said, let's all party together. And that is the Grignard reagent. So a couple of things that I want to continue to talk about as far as the Grignard or the lithium reagents go. And really, this kind of stays true to most of the organometallics, not just Grignards and lithiums, but anything that requires a metal. So the first thing that you have to understand, of course, is that we're using metals. And metals are solids. So not only are we flipping the script on the way organic carbons will work in these cases, and they become carboanions. But folks, we're also talking about solids as well. And these solids are a little bit different than some of the other reagents, even in Orgo 1, all of those reagents and reactions that we studied. And the solids are going to be a little different because this is a completely different state of matter. So we have to handle these a different way. They're just not liquids that can be mixed together and we can throw some heat onto the liquids and then away we go. We get some type of product. So very common when we prep any of these organometallics, Grignards, lithiums, and so forth. There's always a couple of things that we have to go through in their preparation. And number one, we always typically crush those solids. So, for instance, in the Grignard, we'll have these magnesium strips. And those magnesium strips are great. I mean, that's how we order them. That's how we prefer to order them. But if I could crush these, then I could increase the surface area of them. And I could expose more of the area of that particular type of metal. And these reactions typically happen a little bit better because of that. Next, we have to stir these very rapidly. Very often we're cranking our stir plates on to top notch because we want to ensure that the solid will come in contact with those liquids all the time. And if we don't stir them, what happens is that only kind of that top surface of the metal will be exposed to the bottom surface of that liquid, maybe, if that's how you want to look at it. And these different states of matter will take a little bit longer to react and do what we need to do with them. So we constantly stir them and we put them at high speed whenever possible. That ensures that we are creating this tornado effect in our solution and that our solid is coming in contact with our liquids a little bit better. Finally, you would often see someone sonicate. Yes, sonication is a thing that we can do in a lab. So maybe stirring is not the best option. And what we can do is that we can send vibrations through the solution. And that just kind of gets them going a little bit better. They go to the gym, they work out a little bit more. Those sonications, those vibrations is kind of like putting on headphones and listening to your workout music. It gets you in the groove a little bit more. And that's exactly what sonication does as far as these organometallic preps are concerned. So these are typically the things that we would do in an actual laboratory. And you would see this in our very first Grignard that we do together. So I'm going to be talking about crushing metals, about stirring them very fast. We're not going to be using a sonicator. We do have them in our lab, but for that particular purpose, we don't necessarily need to bring it out. 4, we also need you to understand, to be aware that these reactions are typically exothermic. So they do give off heat, but da-da-da-da-da. There we go. It gives off some heat. And it gives off some heat for a number of different reasons. We can talk about bonds breaking and bonds forming, and we can talk about Gibbs and enthalpy and everything else that goes along with it, but we're not going to. That's really more of a general chemistry type of topic. But these are exothermic reactions. We do get heat that's generated from this reaction. However, here's the thing. Very often, we have to put in a little, but we get out more than what we put in. So, for instance, this is not an uncommon thing for a Grignard. Here I have a round bottom bowling flask, and in this bowling flask is maybe an alkyl halide and some Grignard reagent or some magnesium metal, right? We're prepping that magnesium to make a Grignard. So when we do this, we put a stir bar in, we stir it up. We might have to put a little bit of heat into the system in order for it to go forward. And folks, that heat doesn't necessarily have to come from a hot plate. So very often we're using hot plates or something like that as far as our heat source goes. It's not really needed here. This reaction can happen simply due to the generation of heat from your hands. That's all that you need to do. You hold the flask. And that is probably one of the neatest things that we actually do in a lab in organic, I think. We can grab these flasks with these magnesium turnings and with the alkyl halide. And folks, I can put this flask into my hands and cradle it. And that is enough heat for this reaction to start. And all of a sudden, I'm holding this flask and this reaction is starting right in front of me. That's all that we need in order for this to go forward. So literally, I'm almost holding a bowling flask with this reaction that's taking place, and it is getting warmer as I'm holding it. That round bottom is getting warmer and warmer over time, and I would eventually have to put it down because it could get so hot that I can't hold it anymore. But to get this started, you really read directions, and it just says cradle the flask in your hands for a brief moment in time, and then all of a sudden you see this reaction happen in front of you right before your eyes. It's one of the neatest things that happens as far as I'm concerned and as far as many students are concerned in organic labs. So Grignards are very neat labs when we get to do them. They're just different. The carbons are acting different. The metals are incorporated in this. It doesn't take a lot of heat for these things to get started. And just something as simple as holding that flask can just make you remember those types of labs a little bit more. So that's kind of what we go through. Now, one of the other things that we said before is that water's bad. Water is bad because water is going to be concerned or is labeled as an acid. Now, I know what you're going to say. Well, an acid? Why? Water can't be an acid. Yeah, it can. Water can be an acid. Anything with a hydrogen can be an acid if you give it the right pH conditions. You can always get a hydrogen to be spit off of a molecule. It just really depends on how much effort do you got to go through in order for it to spit off the hydrogen. Water is not one of these exceptions, right? Water can act as an acid under the right conditions. Now, this is a very weak acid. And that's the problem with Grignards, because any type of weak acid, folks, is going to react with my Grignard. And this is my Grignard right here. This is what I'm trying to make. This is maybe what I want to use for another reaction. The problem, though, is that if there's any water traces at all, that's the biggest problem. But in addition to this, any type of weak acid as well, this Grignard is going to get destroyed. And I do not want this to happen. Guys, if I'm going to go through this whole concept of making the Grignard reagent, taking the magnesium, taking the turnings, crushing them up, stirring them really fast in a bowling flask, using my alkyl halide in that solution, mixing these things together, getting my Grignard. I'm going to use this Grignard for another reaction that's not shown on the screen, right? The problem is if there's any water traces at all, any water traces, their Grignard will not work. And the reason is that the Grignard gets destroyed. So it never has a chance to react. And this is always the number one that happens in a lab. You know, students get so excited. They take this Grignard, they see it kind of bubbling in their flask, and they're like, we're doing it, we're doing it. And then they add the next part of the procedure into the Grignard, and they go through all of these steps, and at the very end, they test their product, and it is not what it's supposed to be. Oh, that's so pitiful. That's so sad. And the reason, number one reason, water. Water was there. Water was in the glassware because you didn't sufficiently dry it enough. Water was in maybe your solvent that you used because you didn't make sure that it was dry before you used it, or anhydrous. Water was gained from the outside, and it sucked that water moisture in when you made the Grignard. All of these are problems, and water is notorious for destroying a Grignard reagent. Now the question is why? Okay, why does this happen? Well, I told you just now that water could be regarded as a weak acid, which means that water has a hydrogen that it can donate. So here's my water molecule, and that oxygen can take those electrons because it's electronegative. There it goes. And this hydrogen can go off. Well, if this is the definition of an acid, it has to be given conditions where it turns into an acid, which means the other counterpart that it's reacting with, there's my organic, and then off of this maybe is an MgBr. Folks, these are very, very basic. Very basic. Which means this carbon that's right there is a carboanion. It's negative. And it looks at this positive carbon, and it looks at this MgBr. And carbon has a choice. Do I want the Mg, or do I want the hydrogen? And it looks at these two choices, and it does what any other atom does. Like we've talked about in Organic 1, carbon looks at this hydrogen and says, I can have my way with that hydrogen a little bit more than that magnesium. That means this hydrogen is super tiny, puny, a runt, and I can tell it to do whatever I want it to do, and it's going to listen to me. So it's going to go in and it's going to rip the hydrogen off, and when it does that, carbon can't have 5 bonds. So carbon looks at these choices that it has, and to the left, it's going to see another carbon. To the right, it sees another carbon, and then down here below, it sees this metal, this magnesium. So this carbon makes a decision. Magnesium, listen, it was great while it lasted, and thank you for coming around, and thank you for giving me a good time. But boop, off you go. Away. Because I'm getting ready to pull hydrogen in, and I can have my way with hydrogen a little bit better. He's not going to put up a fight. I can basically be the boss of the house, and hydrogen can't say anything about it. So off goes the magnesium, and this water molecule turns into an acid because it is donating the hydrogen that it has. So this water turns into the acid, and what happens is that this MgBr comes off of there, and it does pair up with that OH group, and we get this kind of compound that forms. Well, if this OH group is the acid, well, here's the OH group, right? This would be called the conjugate base. Remember, that goes all the way back to that one of those very first lectures that we had together in Organic 1, and it was about acid-base chemistry. What is an acid? What is a base? What's a conjugate acid? What's a conjugate base? Can we label them? Can we identify them? And one of the things that you have to keep in mind here is that equilibria will happen. These equations will go back and forth, but it lies to the side that has the weakest acid because it's not going to put up a fight anymore. That's why it does that. It's very weak. It's tired. It needs the rest. So these reactions will always gravitate to the side that has the weakest ones. Well, what does that mean? I'll show you an example of this in just a minute. But this is the whole concept of getting these carboanions to react. The metals go on, we form these Grignards. If water is present, and that's our biggest concern, if water's present, water will act as an acid in regards to the Grignard. And that proton is ripped off, that protonates the carbon, that carbon anion, that's why it's attracted to that hydrogen, makes the decision to get rid of MgBr as a leaving group, and that MgBr leaves the molecule and it pairs up with the OH of the water. Now, why is this so important? Well, water's not the only thing that does this, folks. There's a couple of other things that does this too. Anything that could have acidic groups, you have to be very careful with. So OHs are also a problem. NH2s are a problem. What? Well, whoa. NH2s? I thought that we learned in Orgo 1 that NH2s had pKa's of like 40s. And if that was like pH of 40, that would be super, super basic. So you're telling me that NH2s at pKa's of 40s, which in other terms would be regarded as a very strong base, is regarded as an acidic group in the world of organometallic? Yes. That's how powerful these organometallics are. Even amines can donate a proton to these solutions. In addition to that, SH groups, which are our thiols that we learned about in the last lecture, we see the acetylide ions. We talked about acetylides. The acetylide ions happen in the reactions of alkynes that we learned about in Orgo 1. And then, of course, the COOH groups, these are carboxylic acids. Those are also very commonly found in a lab. Those carboxylic acids are acids, of course, because they're called acids. And not only that, but they do not have to be there in large amounts. Because look at what this says. Trace amounts is all that it will take. And folks, this work is destroyed. So I cannot push this fact any more than what I already have. No water, no moisture, nothing acidic. Because when you bring these things in, that will decompose the organometallic that you're using in the world of lithiums and magnesiums, especially in this world. And these things are destroyed, and it's almost like they never even happened. And once again, that's a very Debbie Downer moment. Now, what you're seeing here is a way that they possibly could use this to someone's advantage. So the hydrogen goes into that carbon, and that's why you see a CH2 here, and the magnesium goes off. Off it goes. Pew! But in organic, there are times that we would want to label things. We label things due to maybe somewhat like a radioactive decay or an isotope that we can pick up. A couple of reasons that we would do that. And that's what D2O is. The D stands for deuterium. And deuterium is a heavy, fat little hydrogen. It's an isotope. So it has an extra neutron. Now keep in mind the definition of an isotope. Hydrogen has one electron. Hydrogen has one proton and 0 neutrons. How do we know that? Well, on the periodic table, hydrogen has a 1 up here and a 1.01 down here. This is the proton number. This is also the electron number. 1.01 is the mass number. Okay, well, protons weigh 1. So 1 minus 1, 0. So 0 neutrons is what's left over. Well, what about the O1? These are all the other little crappy subatomic particles that we don't worry about. That's why it doesn't quite match and be a whole number. All right, well, deuterium is a hydrogen that has an extra neutron. It ate a little too much for dinner. And that bigger, heavier hydrogen is an isotope. And that isotope can come around and be detected by equipment. So this D2O is listed here because this is a way that we can easily put on a heavy hydrogen to a molecule. And now we can track where that heavy hydrogen goes. Folks, the discovery of DNA happened with isotopes like this. We were playing around with phosphorus, and we were playing around with sulfur, and we were giving heavy, fat little phosphoruses and heavy, fat little sulfurs to these reagents and reactions, and we were tracking to see what was happening with them. The same thing's happening here, it's just with hydrogen instead. So this allows our equipment to track and record the movement of these molecules and where these maybe reagents go, how these reagents react, where does that hydrogen go? And that also gives us insight to mechanisms as well, which is one of the ways how we determine how these mechanisms happen. All right, so that was kind of a tangent. It was a side note, but that's why they put that onto the slide. Now let's do an example problem. It says, which of the following form products? And then it says the pKa values necessary to solve this problem. See Appendix 1. Recall that the equilibrium favors formation of the weak acid. Hint, 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 section 2.5. So they give me all of these reactions. 1, 2, 3, 4, 5. All right, 1, 2, 3, 4, 5. So they want me to learn a little bit about pKa if I didn't get it the first time around. They want me to use pKa to help me make this decision. And this is their way of showing you how powerful some of these acids are going to be with the Grignard. And I'm saying Grignard because every one of these cases, it's an Mg that they gave us as an example. And they gave us the same Grignard every single time as an example. So the only thing that we're changing here are the reagents that we are adding to the system. And they want to know which one of these would prefer this over here on this side. Which means when I act these two things together, will they give me these products, yes or no? pKa's will help me determine that. This is how easy this is. pKa of water. pKa of water is about a 15. This was one of those pKa's that we learned in Orgo 1 in probably the very first or second lecture. This is an alcohol. Alcohols have very similar pKa values. They have OH groups as well, just like water does. Water's HOH, alcohols are ROH. And they have similar, not exactly the same, but same kind of ballpark figure. That's all that we need here. Well, what about these amines, NH3 and NH2? Well, NH3 and NH2 are amines. We learned about pKa's of amines as well. They're around a 40, 35 to 40, give or take a little bit, depending on what's on them. And what about the acetylide ions? The acetylide ions have a pKa of around 25 to 30, so I'm going to say 25-ish. Notice I didn't need the appendix for this. I'm better than that. You're better than that. These are pKa's that we have talked about in another class. Now, they might have been stored in a filing cabinet with a little bit of dust on them, but now that I've mentioned them, you'll be like, oh yeah, I remember that. I hope so. The part that we would need that appendix for, though, is what's on the other side. Notice in each case, CH3, MgBr, and I have H2O. So here's the H2O, and there's OH. It looks like this has donated a proton, so therefore that is going to be defined as the acid. In my second one, CH3OH. So here's the OCH3 and there's the OCH3. It's lost a proton, so therefore that's the acting acid as well. NH3. Well, it was NH3 in the beginning, and now it's NH2, so it's lost a proton. That's the acid. CH3NH2, and now we have CH3NH. Well, it lost a proton. That's the acid. C triple bond C, both with H's, and here we ended up with C triple bond CH. It's lost a proton, so therefore that's the acid. So what I've circled here are all defined as an acid in the equation, which means if this is the acid, this would be the conjugate base. That's how those work. So by default here, all of these CH4 groups are going to be the acids on this side of the product because these are bases. Every one of those are bases by definition at this point. So the way we solve this problem, I compare the pKa's to the left of that acid to the pKa on the right of those acids. And in each case, the acid is the same, CH4s, all the way down. Well, I need Appendix 1 in the back of your text to look up the pKa's of methane. And I'm going to find out that that pKa is a 60. Those are by definition the acid of these equations with these metals. But it's a pKa of 60. Could you imagine if I said pH of 60? You're going to say, gosh, that's a super base. It's like Nicki Minaj's super base type, right? So the way that we solve this problem, we compare the acid to the left, water, has a pKa of 15, to the acid on the right, which is methane, which has a pKa of 60. Which one of these is a better acid? And you would look at these two numbers and say, well, 15 is lower. And if this was a pH scale, you would say that this was more acidic, which means that this is a stronger acid compared to the 60. That means that this reaction makes product because I'm comparing 15 to 60. This one makes product because that's comparing 15 to 60. This one makes product because even if it's ammonia, that is a 40. That 40 is still lower than 60, which means that's more of an acid than that 60 is. This amine makes product, still pKa of 40-ish, and this acetylide ion also makes product. 25 is lower than 60. It is more acidic, therefore it's stronger. And these reactions always lie to the weakest side. That is how all of these acid-base reactions have always been handled. Okay, so that again proves why these things are problematic. My OHs, my NH2s, my SHs, my acetylides, my carboxylic acids. Folks, even though these might be defined as bases in normal circumstances, compared to a Grignard or a lithium organic, not so much. These are still acidic in the eyes of those organometallic compounds, and they will destroy those reagents before you even get to use them. So that is why it is super, super important for you to remove all water, which is the number one contaminant in these reactions when you do them in a laboratory. All right, so that's where this video is going to stop. That was a little bit about the background and the warning of water. I know I keep saying it, but that's how important that it is to these reactions. So now the question is, once we get our Grignard, okay, so let's say that we have a organic, and off of this organic is my MgBr. Now that I have my Grignard, what can I react it with in order to get some type of product? Well, that's what we're going to talk about next. So in the next video, we're going to pick up from here, And we're going to discuss what types of reagents that I could use in that question mark. What do they expect me to be comfortable with at this point now that I've made this organometallic? And you're going to see that the options are wide open.